Hello, in this lecture we will find the size of line segment AE. In the drawing we have square ABCD, and we know that line segment EB equals to 2 units, line segment DE equals to 8 units, and we want to find out the size of line segment AE. So actually we want to find out the size of this line segment AE in the red color. So first of all we join together points D and B by a straight line. We also know that angle BED, this angle is a right angle, it equals to 90 degrees. Therefore, triangle BED is a right triangle. So I write it down that triangle BED is a right triangle therefore we can use the Pythagoras theorem in the right triangle BED. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In our right triangle, the hypotenuse is side BD, so the square of the hypotenuse it is actually BD square. And it equals to the sum of the squares of the perpendiculars. The sum of the squares of the perpendiculars in the right triangle BED is actually EB square plus DE square. So the implementation of the Pythagoras theorem in the right triangle EBD gives us equation number 1 that states that BD square equals to EB square plus DE square. Okay, so BD square equals to EB square. EB equals to 2 units, therefore EB square is 2 square, 2 square is 4, plus DE square. It is given us the question that DE equals to 8 units, so DE square is 8 square, and 8 square is 64. So in total we got that BD square equals to 4 plus 64. 4 plus 64 is 68. So I found out that BD square equals to 68. Here we will take a root out of equation number 1 and we will get that BD equals to the square root of 68. So we found out that BD equals to the square root of 68. BD, it is actually also the diagonal of square ABCD, and we found out that it equals to the square root of 68. The square root of 68 units. We also know that all the angles inside the square are right angles, therefore angle BCD is a right angle and it equals to 90 degrees. Angle BAD, this angle is also a right angle and it also will be equal to 90 degrees. In the next step I will present to you a new rule and we will implement the new rule in our drawing. So rule number 1 states that the diagonals of a square bisect, or we can use the word also cross, bisect the angles of the square into 45 degrees angles. I will read again rule number 1. Rule number 1 states that the diagonals of a square bisect or cross the angles of the square into 45 degrees angles. So we can implement rule number 1 in our drawing, because in our drawing we have square ABCD and diagonal BD. So according to rule number 1, the diagonal BD bisects the angles of the square into 45 degrees angles. That is to say, angle BDC will be equal to 45 degrees, and also angle BDA will be also equal to 45 degrees. Why? Because actually the diagonal BD divides the angles of a square into two equal angles. And likewise, angle CBD, this angle will be equal to 45 degrees. And angle EBD, angle ABD, this angle will be also equal to 45 degrees, because of the fact that according to rule number 1, the diagonal DB divides the angles of a square into two equal angles. The size of each angle equals to 45 degrees. So this angle equals to 45 degrees, and this angle also equals to 45 degrees, and this angle equals to 45 degrees, and this angle also equals to 45 degrees. So actually triangle BCD is a right triangle because of the fact that angle BCD is a right angle. So triangle BCD is a right triangle. Triangle BCD is a right triangle. We will define side side CD as y. That is to say, CD equals to y. And we actually know that cosinus 45 degrees in the right triangle BCD cosinus 45 degrees equals to DC over DB. I'll repeat again. In the right triangle BDC, cosinus 45 degrees equals to DC over DB. But we define DC as y, so we will substitute DC by y, and we have already found out that the diagonal DB equals to the square root of 68 units. So in total we got that cosinus 45 degrees equals to y over square root of 68 units. So cosinus 45 degrees going into equation number 2 equals to y over square root of 68 units actually cosinus 45 degrees is actually square root of 2 over 2, so we substitute cosinus 45 degrees by square root of 2 over 2, and it equals to y over square root of 68 units according to equation number 2. Here we will multiply equation number 2 by square root of 68, and we will get that y equals to the square root of 68 times square root of 2 over 2. Okay, so we multiply the equation number 2 by square root of 68, and we found out that y equals to the square root of 68 times square root of 2 over 2. We know that 68 equals to 34 times 2, so we'll substitute 68 here inside the root by 34 times 2. We will get that y equals to, so 68 is 34 times 2, times square root of 2 over 2. Okay? Now we have a rule that states that the square root of a times b equals to the square root of a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2 and we also will have to multiply it by the square root of 2 over 2 and it equals to y according to equation number 2. We know that square root of 2 times square root of 2 equals to 2, so we will write it down. So y according to equation number 2 equals to the square root of 34 and square root of 2 times square root of 2 is 2 over 2. 2 over 2 is 1, so 2 will get cancelled and we actually found out that y equals to the square root of 34 units. Okay, and y it is actually the size of the size of square ABCD, one side of square ABCD, the size of side DC of square ABCD, and we also know that all the sides of a square are equal to each other, so DC equals to the square root of 34 units, and also BC will be equal to the square root of 34 units. AB equals to the square root of 34 units. And AD equals to the square root of 34 units. Okay, so we actually know the values of all the sides and line segments in this drawing, and the only missing variable is the size of line segment AE that we are looking for. So in the next step I will present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, Rule number 2 states that if line segment AB if a line segment AB subtends two equal angles, on the same side, then the quadrilateral ABCD is inscribed by a circle and the 4 points A, B, C, and D lie on that circle. Well, I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So, what is the meaning of rule number 2? The meaning of rule number 2 is actually if we have line segment AB so this is line segment AB I will repeat again. This is line segment AB, and line segment AB subtends two equal angles. So the first angle So angle ACB subtend on line segment AB, and it equals to theta. And we also have second angle that also subtend on line segment AB. Actually, angle ADB also subtend on rest on line segment AB, and it also equals to theta. So actually in this drawing we have two equal angles that subtend on the same line segment AB. Okay, so if this is the reality, then we have two equal angles that rest on line segment AB, or two equal angles that are both equal to theta subtend on line segment AB. So if this is the reality, then according to rule number 2, the quadrilateral ABCD, this quadrilateral ABCD this quadrilateral ABCD is inscribed by a circle. So quadrilateral ABCD is inscribed by a circle. So as you can see from the drawing, quadrilateral ABCD is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. So I will repeat again on rule number 2. If we have line segment AB and we have two equal angles that rest on the same line segment AB, then the quadrilateral ABCD, this quadrilateral is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle, and indeed, as you can see from the drawing, those 4 points A, B, C, and D lie on this red circle. Okay. I will repeat again. We started from line segment AB, and we had two equal angles. Those two equal angles, they are both equal to theta, that rest on the same line segment AB. Therefore, according to rule number 2, this quadrilateral ABCD is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. Okay, so we can actually implement rule number 2. This is the implementation of rule number 2, or this is the explanation of rule number 2, and we can implement rule number 2 in our drawing. Why? Because in our drawing we have those two right angles rest or subtend on the same line segment BD. So I write it down. We have angle BAD, this angle that equals to 90 degrees. This angle subtend on line segment BD. I will repeat again, angle BAD is equals to 90 degrees, subtend on line segment BD. And we also have second angle. This angle, it is also a right angle or angle BED. Angle BED also equals to 90 degrees. And it also subtends on line segment BD. I will repeat again, angle BED that equals to 90 degrees, this angle equals to 90 degrees according to what is given us the question. Angle BED that equals to 90 degrees also subtends on line segment BD. As you can see, angle BED subtends or rests on line segment BD. Therefore, according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So actually, the quadrilateral AEBD in the red color, in the green color, the quadrilateral that I paint in the green color, quadrilateral AEBD, subtend the quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So I write it down that according to rule number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So the quadrilateral in the green color, quadrilateral AEBD, is described by a circle, and the 4 points A, E, B, and D lie on that circle. So we will draw the implementation of rule number 2 in our specific drawing. So actually we have quadrilateral AEBD, quadrilateral AEBD is inscribed, the quadrilateral in the green color, quadrilateral AEBD is inscribed by a circle, so the quadrilateral AEBD is inscribed by this blue circle. I will paint it in the green color. This is quadrilateral AEBD. That it is inscribed by the blue circle. The quadrilateral in the green color AEBD is inscribed by this blue circle, and the 4 points AEBD lie on this blue circle. And why? Because we have two right angles that lie on line segment BD. So we have angle ABD, angle ABD. This angle is a right angle. This angle, angle ABD, is a right angle, and this angle rests on line segment BD. And we also have the second angle, angle BED. This angle, angle BED, it is also a right angle, I will repeat again. This angle, angle BED, it is also a right angle, and angle BD rests also on line segment BD. So we have those two right angles, they are both rest on line segment BD. Therefore, according to rule number 2, the quadrangle AEBD in the green color rests. The quadrangle AEBD is described by this blue circle, and the 4 points AEBD lie on this blue circle. Okay, so actually this drawing is the implementation of rule number 2 in our original drawing. We implemented rule number 2 in our original drawing, and we got this drawing. So this is according to rule number 2. I will repeat again. Because of the fact that we have two equal angles, those two angles are both right angles and they rest on the same line segment BD. Therefore, according to rule number 2, the quadrangle AEBD in the green color is described by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, we actually implemented rule number 2 in our original drawing, and we got this drawing. Okay, it is the implementation of rule number 2 in our drawing. Okay, so we actually have here quadrangle AEBD that it is described by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay. In the next step, I will present to you rule number 3, and we will also implement rule number 3 in this drawing. So, rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the diagonals of its diagonals, the product of its diagonals equals to the sum of the products of its opposite sides. I will repeat Rule number 3 again. Rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have quadrilateral ABCD, that it is inscribed by this blue circle, quadrilateral ABCD So you can see from the drawing we have quadrilateral ABC in the red color, and it is inscribed by this blue circle. We will define the size of side AC of quadrilateral ABCD as A. That is to say, side AC equals to A units in its size. We will define side CD of quadrilateral ABCD as B, and then we define side BD of quadrilateral ABCD as C, and we define side AB of quadrilateral ABCD as D, that is to say AB equals to the units in its size, and also quadrilateral ABCD has two diagonals. The first diagonal is diagonal AD, and we will define the size of diagonal AD as X, that is to say AD equals to X units in its size, and quadrilateral ABCD has also second diagonal, diagonal BC. So we define the size of diagonal this BC as Y, that is to say BC equals to Y units in its size. So if we have quadrilateral ABCD that it is inscribed by this blue circle, then according to rule number 3, the product of its diagonals, that is to say X times Y, equals to the sum of the product of its opposite sides. Actually, quadrilateral ABCD has two pairs of opposite sides. Side AB is opposite to side CD, and side AC is opposite to side BD. And the first product of its opposite sides, it is actually the size of AB times the size of CD. This is to say B times D. That is the first product of its opposite sides, and the second product of its opposite sides is the size of side AC times the size of side BD. That is actually A times C. So, and the sum of the product of its opposite sides, it is actually BD plus AC. So the sum of the product of its opposite sides, that is actually BD plus AC, equals to the product of its diagonals, that is actually X times Y. Okay, so according to rule number 3, the product of its diagonals that is actually X times Y equals to the sum of the products of its opposite sides. The first product of its opposite sides is B times D. The second product of its opposite sides is A times C, and the sum of the products of its opposite sides is BD plus AC, and that sum of the products of its opposite sides equals to the products of its diagonals, that is actually X times Y. Okay, again, the product of its diagonals, that is actually X times Y, equals to the sum of the products of its opposite sides, that is actually BD plus AC. Okay, so that is rule number 3, and we will actually implement rule number 3 in our drawing. We actually arrived to this drawing by implementing rule number 2 in the original drawing. We arrived to this drawing, and actually we have here quadrilateral AEBD that it is inscribed by this blue circle. So whenever we have quadrilateral that it is inscribed by a circle, we can implement rule number 3 in that drawing. So because of the fact that we have quadrilateral AEBD that is inscribed by this blue circle, we can implement in this drawing rule number 3. And according to rule number 3, the product of its diagonals, that is actually AB times DE, AB times DE, AB times DE, the product of quadrilateral AEBD diagonals is actually AB times DE, and that product of its diagonals equals to the sum of the products of its opposite sides. Side AE of quadrilateral ABCD of quadrilateral AEBD, side AE is opposite to side BD, and side AD is opposite to side EB. So the first product of its opposite sides, it is actually AE times DB. AE times DB is the first product of its opposite sides. And the second product of its opposite sides, it is actually AD times EB. And the sum of the product of its opposite sides is the first product plus the second product, or AE times DB plus AD times EB, that is the sum of the product of its opposite sides. The sum of the product of quadrilateral AEBD opposite sides. And that the sum of the product of its opposite sides equals to the product of its diagonals, that is actually AB times DE. Okay? So AB times DE, that is the product of its opposite sides, equals to the sum of the product AB times DE, that is actually the product of its diagonals. AB times DE, that is the product of its diagonals, equals to the sum of the products of its opposite sides, that is actually AE times DB plus AD times EB. So that is actually equation number 3. And the question number 3 is the implementation of rule number 3 in our drawing. Okay, the implementation of rule number 3 in our drawing gives us equation number 3. Okay, AB times DE equals to AE times DB plus AD times EB. Okay, so I will repeat on rule number 3 again. According to rule number 3, if quadrilateral ABCD is described by a circle, in our case we have quadrilateral AEPD that is described by this blue circle, then the product of its diagonals, then the product of diagonals AEBD, it is actually AB times DE, AB times DE equals to the sum of the products of its opposite sides. And the sum of the product of its opposite sides is actually AE times DB, AE times DB plus AD times BE plus AD times EB or BE, it is the same. So the product of its diagonals, that is actually AB times DE, equals to the sum of the product of its opposite sides, that is actually AE times DB plus AD times EB. Okay? So the only thing that is left to do, actually I will repeat again that if we have quadrilateral, any quadrilateral that is inscribed by a circle, we can implement rule number 3 in that quadrilateral. And here we have quadrilateral AEBD that is inscribed by this blue circle, therefore we can implement rule number 3 in this drawing. And according to rule number 3, the product of its diagonals, that is to say AB times DE, equals to the sum of the products of its opposite sides. That is to say AE times DB plus AD times EB. Okay? The product of its diagonals, that it is AB times DE, equals to the sum of the product of its opposite sides, that is actually AE times DB plus AD times EB. Okay? I'll repeat again. Equation number 3 is the implementation of rule number 3 in our drawing, in this drawing. Okay? So now we will find out the values of all the variables inside this equation number 3. AB equals to the square root of 34. DE equals to 8 units. Therefore, AB equals to square root of 34 and DE is 8 units, and all equals to AE. AE is the missing line segment, so we will leave it as it is. Times DB. DB equals to square root of 68. So in the other side of the equation number 3, AE is AE and DB equals to square root of 68 plus AD equals to square root of 34, and EB equals to 2 units. It is given us in the question that EB equals to 2 units. I'll repeat again. AD equals to square root of 34 and BE or EB equals to 2 units. It is given us in the question. So here we have square root of 68. 68 is 34 times 2, so I will write it down. Instead of 68, I will add down 2 times 34 plus square root of 34 times 2 and according to the rule that the square root of A times B equals to the square root of A times square root of B, the square root of 2 times 34 will be equal to the square root of 2 times square root of 34, and all the rest is S3. It's like we will not change all the other variables, all the other things in this equality. We change only this expression by the rule that the square root of A times B equals to the square root of A times square root of B, and the other expressions remain as they are, as they were. So here we will divide the equation number 3, this equation, by square root of 34. So square root of 34 will get cancelled. And what is left after we cancel the square root of 34? What is left is actually, here is 8 equals to square root of 2 times AE plus 2. Okay, here we will subtract 2 from equation number 3 and we will get that 8 minus 2 is 6. 6 equals to the square root of 2 times AE. So here we will divide equation number 3 by square root of 2 and we will get that AE equals to 6 over square root of 2 So actually found out that AE equals to 6 over square root of 2 units. We know that 6 is 3 times 2, so I'll write it down. AE equals to, instead of 6, I will write down 3 times 2 over square root of 2 So here we will multiply this expression by square root of 2 and then we will divide it by square root of 2, so we change nothing. So it is 3 times 2 over square root of 2. We will multiply the expression by square root of 2 and then we will divide it by square root of 2. So AE equals to this expression. In the denominator, here we have square root of 2 times square root of 2 is 2. So I write it down that AE equals to 3 times 2 times square root of 2, and in the denominator we have 2. So 2 over 2 is 1, so 2 will get cancelled. And we found out that AE equals to 3 times root 2 units, or in terms of numbers, AE equals to 4.243 units. So the answer to the question is that line segment AE, this line segment in the red color, equals to either 3 times root 2 units, or in terms of numbers, line segment AE equals to 4.243 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the size of line segment AE. We know that we have here square ABCD. The size of line segment EB is 2 units, the size of line segment DE is 8 units, and angle BED, this angle is a right angle, and we want to find out the size of line segment AE. Okay, so first of all, we join points B and D by straight line, and actually triangle BED is a right triangle, so we can implement the Pythagoras theorem in the right triangle BED. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. And in our specific right triangle, the right triangle BED, the hypotenuse is actually side BD, so the square of the hypotenuse is BD square, and it equals to the square of the hypotenuse equals to the sum of the squares of the perpendiculars equals to EB square plus DE square. So in the right triangle BED, the square of the hypotenuse is BD square, and it equals to the sum of the squares of the perpendiculars equals to EB square plus DE square. We know that EB equals to 2 units, so EB square is 2 square, 2 square is 4, DE equals to 8 units. This is given us the question, so DE square is 8 square, 8 square is 64. 4 plus 64 is 68, so we got that DB square equals to 68. We took a root out of equation number 1 and we got that DB equals to square root of 68. So we found out that the diagonal of square ABCD DB equals to square root of 68 units. And then I presented to you rule number 1. According to rule number 1, the diagonals of a square bisect or cross the angles of the square into 45 degrees. So we can implement rule number 1 in our drawing, because in our drawing we have square ABCD and the diagonal BD. According to rule number 1, the diagonal BD bisects the angles of the square, that is to say, angle BDC will be equal to 45 degrees and angle ADB will be also equal to 45 degrees. And here the diagonal BD bisects this angle, that is to say, this angle will be equal angle DBC will be equal to 45 degrees, and angle ABD will be also equal to 45 degrees according to rule number 1. Okay? And we know that all the angles inside the square are right angles, therefore this angle equals to 90 degrees, it is a right angle. So therefore triangle BCD is a right angle, and we defined side DC of the right triangle, triangle BCD is Y, that is to say this equals to Y. So in the right triangle, triangle BCD, we know that cosinus 45 degrees equals to DC over DB. Cosinus 45 degrees in the right triangle, triangle BCD equals to DC over DB. Okay? But DC equals to Y units according to our definition, and we have already found out that DB equals to the square root of 68 units. So we substituted DB by square root of 68 units and DC by Y. And we got that cosinus 45 degrees according to equation number 2 equals to Y over square root of 68. And we also know that cosinus 45 degrees equals to the square root of 2 over 2. So we substituted cosinus 45 degrees by square root of 2 over 2, and it equals to Y over square root of 68. We multiplied the equation number 2 by square root of 68, and we found out that Y equals to the square root of 68 times square root of 2 over 2. We also know that 68 equals to 34 times 2, so we substituted 68 by 34 times 2. And according to the rule that the square root of A times B equals to the square root of A times square root of B, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. So in total we got that Y equals to the square root of 44 times square root of 2 times square root of 2 over 2. And we know that the square root of 2 times square root of 2 is 2. So in total we got that Y equals to the square root of 34 times 2 over 2. 2 over 2 is 1, so 2 will get cancelled, and we got that Y equals to the square root of 34 units. So Y equals to the square root of 34 units, and we know that all the sides of a square are equal to each other, so all the sides of square ABCD will be equal to the square root of 34 units. Side BC equals to the square root of 34 units, side AB of square ABCD equals to square root of 34 units, and side AD of square ABCD equals to the square root of 34 units, and of course side DC also equals to the square root of 34 units. Then I presented to you rule number 2. According to rule number 2, if a line segment AB subtend two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So we have line segment AB, and we have also two equal angles. Those two angles are both equal to theta, and they both subtend on the same line segment AB. Angle ADB, this angle subtends on line segment AB, or angle ADB rests on line segment AB, and angle ACB, this angle subtends or rests on line segment AB. So we have two equal angles that are both rest on the same line segment AB. Therefore, according to rule number 2, the quadrilateral ABCD, this quadrilateral, is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. Okay, this is the explanation of rule number 2. And we can implement rule number 2 in our drawing. Because in our drawing we have those two right angles, they are both subtend on the same line segment DB. Okay, those two angles, this angle is angle BAD, it is a right angle, and it is subtend or rest on line segment DB. This angle BAD, is a right angle, and angle BAD rests on line segment BD. So we have two equal angles that rest on the same line segment DB. Therefore, according to rule number 2, the quadrilateral AEBD is described by a circle, and the 4 points A, E, B, and D lie on that circle. Okay, I'll repeat again. Angle BAD equals to 90 degrees, and it subtends on line segment DB. Angle BAD, this angle equals to 90 degrees, and it subtends on line segment BD. Angle BED also equals to 90 degrees, and it also subtends on the same line segment BD. This angle, it is a right angle, and it rests on line segment BD. So we have two equal angles that rest on the same line segment BD. Therefore, according to rule number 2, the quadrilateral AEBD, is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. Okay, so I'll repeat again. We have those two angles, they are both equal angles, they are equal to 90 degrees, and they subtend on the same line segment BD. Angle DAB, that is a right angle, it rests on line segment BD, and angle DEB, that is also a right angle, it also subtends on the same line segment DB. Therefore, according to rule number 2, the quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle, and indeed those 4 points A, E, B, and D lie on this blue circle. So this is actually the implementation of rule number 2 in our drawing. Okay? And we also presented to you rule number 3, and we implemented rule number 3 in our drawing. According to rule number 3, if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So, what is the meaning of rule number 3? The meaning of rule number 3 is that if we have this quadrilateral ABCD that it is inscribed by this blue circle. So whenever we have quadrilateral that is inscribed by a circle, we can implement rule number 3 in that drawing. So okay, here we have quadrilateral ABCD that is inscribed by a circle, therefore we can implement rule number 3 in this drawing, and according to rule number 3, the product of quadrilateral ABCD diagonals, it is actually x times y, and it equals to the sum of the products of its opposite sides. The first product of its opposite sides is b times d, the second product of its opposite sides is a times c, and the sum of the product of its opposite sides is b times d plus a times c. And that sum of the product of its opposite sides equals to the product of its diagonals, that is actually x times y. So x times y, that is the product of its diagonals, equals to the sum of the products of its opposite sides, that is actually bd plus ac. And we actually also implemented rule number 3 in our drawing. First of all, we arrived, this is the original drawing, and from this original drawing we arrived to this drawing by implementing rule number 2 in the original drawing. We have here two equal angles that subtend on the same line segment BD, therefore according to number 2, the quadrilateral AEBD is inscribed by a circle, and the 4 points AE, B and D lie on that circle. Okay? Because of the fact that we have two equal angles, they are both right angles that subtend on the same segment line BD, therefore the quadrilateral AEBD is inscribed by this blue circle, the 4 points AE, B and D lie on that circle. So this drawing is the implementation of rule number 2 in our original drawing. Now we will implement rule number 3 in this drawing. We will ask the question if we can implement at all rule number 3 in this drawing. And the answer to the question is that we can implement rule number 3 in this drawing, because whenever you have quadrilateral that is inscribed by a circle, you can implement rule number 3 in that drawing. So we have here quadrilateral AEBD that is inscribed by this blue circle, therefore we can implement rule number 3 in this drawing. That's all. Okay, so according to rule number 3, the product of quadrilateral AEBD diagonals, that is actually AB times DE. The product of quadrilateral AEBD diagonals is AB times DE, and according to rule number 3, that product equals to the sum of the products of its opposite sides. And the sum of the product of its opposite sides, the first product of its opposite sides is AE times DB. AE times DB is the first product of its opposite sides, and the second product of its opposite sides is AD times BE. The second product is AD times BE, and according to rule number 3, the sum of the product of its opposite sides, that is product 1 plus product 2, equals to the product of its diagonals, that is actually AB times DE. So AB times DE, that is the product of its diagonals, equals to the sum of the product of its opposite sides, that is actually AE times BD plus AD times EB. So equation number 3 is the implementation of rule number 3 in our drawing, in this drawing. Okay, so the product of its diagonals, the product of quadrilateral AEBD diagonals is AB times DE, and it equals to the sum of the product of its opposite sides. This is actually AE times DB plus AD times EB. AE times DB plus AD plus times EB. The product of its diagonals, that is AB times DE, equals to the sum of the products of its opposite sides. This is actually AE times DB plus AD times EB. Okay, then the only thing that is left to do is to put the data inside this equation number 3. We know that AB equals to the square root of 34 units, DE equals to 8 units. This is given as the question. AE is the missing line segment that we are looking for. DB equals to the square root of 68 units, AD equals to the square root of 34 units, and EB equals to 2 units. It is given us the question that EB equals to 2 units. And here we know that 68 is 34 times 2, so we substituted 68 by 34 times 2. The all other things in this equation number 3 remain as it was. We changed nothing. The only thing that we changed is that we changed 68 by 34 times 2. And we have the rule that the square root of a times b equals to the square root of a times square root of b. And according to that rule, the square root of 2 times 34 will be equal to the square root of 2 times square root of 34. The other things remain as they were. And here we divided the equation number 3 by square root of 34. And what is left after we divided the equation number 3 by square root of 34? What is left is that it is actually 8 equals to the square root of 2 times AE plus 2. Here we subtracted 2 from equation number 3 and we got that 8 minus 2 is 6, so 6 equals to the square root of 2 times AE. So we got that AE equals to 6 over square root of 2. We know that 6 is 3 times 2, so we substituted 6 by 3 times 2. And we got that AE equals to 3 times 2 over square root of 2. Here we multiplied this expression by square root of 2 and then we divided it by square root of 2, so we changed nothing. So it is allowable to do it. And we got this expression. And in the denominator we have square root of 2 times square root of 2. Square root of 2 times square root of 2 is 2. So we got this expression. And 2 over 2 is 1, so 2 will get cancelled, and we found out that AE equals to either 3 times square root of 2 units. This line segment AE in the red color equals to either 3 times root 2 square units, or in terms of numbers, AE equals to 4.243 units. I repeat again, AE equals to either 3 times square root of 2 units, or in terms of numbers, line segment AE equals to 4.243 units. Okay, thank you very much.